So in the first part of this lecture, we looked at the rediscovery of concrete and its evolution into what today we call reinforced concrete, a hybrid construction that takes the compression strength and fire resistance of concrete and sort of marries it to the tensile resistance, the tensile strength of iron or steel. And we had looked in particular at this one building, the first concrete skyscraper, the Ingalls building in Cincinnati by Ernest Ransome, with these local architects, Elzner and Anderson. And when this building was published, there's an interesting quote that Elzner, the local architect, comes up with, where he really defines the moment in an interesting way. He says the skyscraper problem still remains unsolved. The skyscraper is still a new architectural type. We don't quite know what we're doing with it. And he defines it in terms of materials. He says that steel is vulnerable to fire. So building laws very properly, he says, require that we dress it up, right? We have to put another material around it. So we can't actually see the steel. The visible architecture of the steel skeleton building will always be a sham construction, he says. Concrete, he thinks, offers an opportunity, right? Because you can actually see the material that's doing the work. Now, you can't see all of the material. You can't see the reinforcing. But he says that there should be, anyway, a kind of honesty in seeing the actual constructive material that is holding the building up. So to Elzner and to some of the other figures that we've looked at, concrete presents an opportunity to bring a kind of integrated approach where the architecture can emerge from the engineering. You can look at the material, you see what it's doing. The concrete can take forms that tell you something about its structure or about the way it's put together. We'll look at a couple of figures for the rest of the lecture who really kind of think about this and try to come up with a new architectural approach in addition to occasionally a new engineering approach, right? Trying to figure out what concrete means for the profession. The first one, the one who takes the sort of earliest and most complete look at what concrete's potential as a new architectural material is a French first student named Tony Garnier in 1904, so about the time that the Ingalls building is going up. Garnier does a thesis project at his university for a city, an industrial city, in Cite Industrielle. And to Garnier, the future of urban planning, the future of urban design, the future of industry is all wrapped up with this modern wonder material, reinforced concrete. He comes back to it 13 years later, redoes the project as a publication, where it's basically a sort of like an evangelism for reinforced concrete. Here are all the things that this new material can do, arguing for it as the basis for a kind of new approach to design, to architecture at all levels. You can see from his drawings that he's interested both in the technology. So on the far right, this little bus station you can see is very clearly a beamless slab. It has a mushroom column at the top that's trying to take the load of that very heavy roof slab and get it into a very narrow concrete column. But he's also interested in the potential for civic expression. So the city hall that's in the back here is rendered in a sort of stripped down classical form. And we'll see this a lot, that concrete lends itself both to the kind of curvilinear forms of engineering and of traffic and of structural shapes and forms. It also lends itself to the trabeated construction, the beam and post construction that we see in classical architecture. And this tower that's just to the left represents for Garnier, I think, the potential of concrete to achieve new both monumentality in terms of making a civic landmark and new heights, right? A new achievement structurally. For Garnier, the technology is applicable everywhere. And here on the left, you can see his drawings very clearly borrowing from some of the reinforcing drawings that Ransome is doing, that Onabik is doing. And it applies for him at every scale. So on the left, this is an industrial building. On the right, you can see a small-scale single-family house. And for Garnier, concrete is valid for all of these scales, all of these programs, and it can be manipulated to create ornaments or forms that are appropriate to anything from a giant factory a slaughterhouse, a shipbuilding building. All of these things appear in the Cite Industrielle, along with all of this housing, apartment houses, but also, as you can see, single family or middle class housing. And Garnier is pointing out that you can get the ornament that's appropriate to a front stoop or to a garage or to a windowsill or to a chimney, just as you can get the long spanning forms that are appropriate to a factory. Others fall on side of one side of the fence or the other. For Eugene Freyssinet, a French engineer who is commissioned to build these gigantic airship hangars at Orly Airport, concrete is perfect because it can be built repetitively using formwork that can be used again and again and again. The airship hangars have a catenary shape, so they are shaped like the inverse of the chain. This goes back to Hooke and Wren. It goes back to Polanyi and his analysis of St. Peter's. You can see in the drawing on the right that Freyssinet is making these out of hollow trapezoidal sections. And because concrete is so fluid, it can make any shape you can form. So Freyssinet says that this hollow section is going to be able to take lateral loads because it has some depth, but because it's hollow, it doesn't have anywhere near the weight that a solid concrete or a solid masonry arch of that scale would have. The catenary shape is achievable by building a single piece of formwork. You can see the truss shape on the interior. That's the scaffolding on which the formwork is applied. It's a complicated shape. It's very difficult to build that shape out of timber or out of steel, whatever Freyssinet is using for the scaffolding. But Freyssinet argues you only need to use it once. You only need to build it once, and you can use it then again and again and again and again. And here, this construction shot shows the traveling formwork. Very complicated catenary shape that allows Freyssinet to build one arch at a time, and the formwork literally travels down the length of the hangar, sort of building an arch as it goes. And Freyssinet says you can just do this infinitely, right? As long a hangar as you need, you just keep building arches, you keep using the same formwork, and there's an economy there. You've invested a great deal in that one piece, but because concrete can be poured again and again and again using the same formwork, there's an economy in reusing that difficult formwork over and over. And just for comparison, right, here's Polanyi's drawing of St. Peter's. Very, very similar catenary shape, funicular shape. Here, achievable relatively simply compared with the masonry dome in this new material of concrete. One of the most versatile designers in concrete is a Swiss engineer named Robert Maillart. Maillart is best known for these bridges, which we'll come back to here in a second. But he's maybe as important for his investigations into the beamless slab, right? How do you get heavy floor slabs to stand on relatively narrow columns? Maillart is a designer, but he's also a kind of experimenter, very much in the Fairbairn tradition, only now with reinforced concrete instead of with iron. And you can see on the right a comparison of his system of reinforcing on the bottom with cap turners on the top. And Maillart is trying to get away from the kind of custom shapes that Turner has come up with, the conical circular formwork that's designed to take the shear load between the slab and the column using the strength of steel. Maillart's version of the beamless slab involves a grid of reinforcing bars that simply get denser and denser, thicker and thicker rebar as you get closer and closer to the columns where the stresses are greatest. And he argues that this is easier on the job site because you can just simply order 10 different thicknesses of rebar, and all it takes is organizing where they go. You don't need special conical formwork to be fabricated in the shop. You can see his experiments here on the left, where he's loading up slabs with sandbags. And then on the bottom, you can see he's using these early electric devices to measure the deflection of the slab, to see if he can figure out how the loads are traversing through the slabs by looking at an actual construction of it. Maillart's warehouses and factories are borrowed certainly from Ransome systems, from Onnabeek systems, but as you can see on the right, they also borrow from Turner's idea about the beamless slab or the flat slab. On the right, this is a multi-story warehouse, and you can see that even though he can't quite get to a pure junction between just a column and just a slab, the mushrooms are relatively small and pretty acceptable in terms of the space they take up. You can see too that the columns get thicker and thicker and thicker as you go down the building. So the lower floors are on the bottom, upper floors are the photograph on the top. And because concrete relies on formwork, you can just make the formwork smaller, or you can nest the formwork to make smaller columns on the upper floors. And that reflects the fact that the columns on the lower floors, of course, are carrying more load because it's like a river, right? The loads from each floor flow into the column. The columns on the bottom are going to be carrying the loads of all the floors above them, and so they have to get quite thick. In iron construction, there's a problem with trying to get the steel columns to line up perfectly and to rivet them to one another in a way that loads flow from one floor's columns into the next. In concrete, you just have to make sure that the center of the formwork is the same at each level, right? And so this is a measure of concrete's versatility, that you can make different shaped columns or different size columns with relative ease. And maybe the most elegant of Maillart's built beamless slabs is this little train depot, right? So the train sheds that we looked at a couple of lectures ago, here is Maillart's version of that using the tools and the construction types that he has to hand. And you can see that he's getting quite close, that the flares or the mushrooms at the top are relatively small, the columns are skinny, the slab is thin, and he's very, very close to getting what he would think of as the beamless slab. Maillart, though, was also interested in concrete expression, and he won a series of bridge commissions throughout Switzerland that we can relate back to the invention of the automobile and the fact that Switzerland is a mountainous country, right? All of these places where cars need smoother transitions between slopes than horses do, and so there's a whole construction program in Switzerland of trying to build roads through mountainous territory. And Maillart gets commissions for many of these bridges. And what he investigates is the way that concrete, which is a stiff, relatively brittle material, can be combined with steel, which of course is very ductile, to give bridges the kind of flexibility they need to take dynamic loads. So imagine a truck rolling over a bridge. Any bridge that is loaded is going to deflect a certain amount. If the bridge can basically bend and not break, it's going to be easier on the foundations. It's also going to be healthier for the bridge structure itself. And Maillart wants to find ways that concrete can take advantage not only of steel's strength, but also of its ductility. And his solution is to try to find ways to create pin connections in concrete. The bridge decks that he designs rely on a principle of connecting basically the deck, treating that as one maybe flange of the bridge span, with a beam arch below, a shallow arch that goes into bending, and because it's in bending requires a great deal of depth to carry the load across a river, right, or a valley. In some cases, as in on the right, Maillart has enough vertical dimension that the arch can function as a pretty true arch. In other cases, like the shallow crossing on the left, the arch has to function as a beam arch. There's no way to get the height that would make the arch function in more or less pure compression. And when this happens, Maillart basically realizes that you can combine the arch with the deck by creating a web in between. And he calls this the hollow box arch, where the entire bridge structure, not just the arch itself, gets recruited into carrying the load across these valleys. And what you end up with are these very, very unique shapes where the spanning component of the bridge is sort of an arch, but sort of a beam. And in this case, you can see that in the center of the span, Maillart designs a hinge, right, so that the bridge can flex a little bit. There are also hinges at the supports so that the foundations won't get twisted out of the ground as the bridge deflects. In between there, though, you can see that the arch, the three-hinged arch, gets very, very thick at its kind of midpoint and very, very thin towards the pins. And that reflects the fact that the arch is also in bending, that it's not just purely in compression. And the thickness and the connection with the deck above are designed to make a form that works partly in compression, partly in bending, and as you can see from the pins, also provides some ductility to the bridge, almost like a fuse to keep the bridge from, the concrete, the parts of the bridge from cracking. When you look kind of inside at Maillart's reinforcement, you can see that he's using these meshes that were originally patented by Monnier some 50 or 60 years beforehand, and those are spreading the various stresses that the beam arch is undergoing throughout the entire section. On the right, you can see a lateral support. This is toward the abutments. And here too, the bridge needs some ductility in the opposite direction, right? The short direction. If you have a truck on one side of the bridge wants to bend a little bit towards that side. You can see in the reinforcing detail that this is very clearly a hinge connection where the steel is providing some ductility, allowing the concrete to bend a little bit instead of breaking. All of that to say, though, that Maillart is also clearly interested in the aesthetic possibilities here. And at Salginatobel, the bridge that we've been looking at here for a little bit, he's exploiting concrete not only for its structural purposes, all of these things that when you combine it with steel, it can do to solve the problem. He's also very clearly interested in expressing that, in showing, just as Gustave Eiffel was doing with his bridges, not just finding pure structural shapes, but thinking of ways to tweak the materials, to tweak the constructions, to make it into a story, right? To tell the story about the structure in addition to solving the problem. In the final part of the concrete lecture, we'll look at a family firm in Paris that takes a very, very different view of concrete. That instead of thinking about just the kind of structural expression that's latent in concrete, that looks at the way that concrete is actually formed, finds a very, very different language in the formwork that they use to build the concrete, and makes almost the exact opposite argument to Maillart in thinking about what concrete wants to represent, what sort of forms it wants to hint at or remind us of, and to come up with a very, very different language that they think is much more appropriate to this brand new material.